The sun just unleashed its most intense burst of activity in months, and the timing couldn't be more perfect for anyone hoping to catch a glimpse of the aurora. A sunspot region that's been quietly building for days suddenly erupted with a flare nearly powerful enough to cross into the most extreme category. Scientists use, and it didn't stop there, multiple eruptions, an approaching solar wind stream, and now 2 separate coronal mass ejections are all converging on Earth within the same 48-hour window. And NOAA has already issued a geomagnetic-storm watch to match. Let's start with exactly what triggered this spike, because the sunspot region behind it has been building towards something like this for a while. Active region 4513 erupted with an M6.9 class solar flare on August 25th, peaking right around 6 in the morning Eastern Time. To put that number in context, solar flares are ranked on a scale running from A through B, C, M, and finally X, with each full letter category representing roughly 10 times more energy released than the one before it. An M6.9 flare sits right at the upper edge of the M-class range, meaning it came remarkably close to crossing into X-class territory, the most extreme classification scientists use for solar eruptions. That flare alone triggered a moderate radio blackout, and it was quickly followed by a barrage of additional M-class eruptions from the same region over the following 24 hours, 5 separate M-class flares in total during that stretch alone. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of space weather coverage reach more people who want to actually understand what's happening above us. Here's why this particular region has scientists paying such close attention. Active region 4513 has been classified with a beta-gamma delta magnetic configuration, a designation solar physicists use to describe sunspot groups with genuinely complex and highly unstable internal magnetic fields. That kind of magnetic complexity is precisely what makes a region capable of producing not just moderate M-class flares, but potentially the far more powerful X-class eruptions as well. And it's exactly why forecasters have kept a continuous 55% probability attached to further R1 or R2 radio blackouts, and a 15% chance of something even stronger through the following several days. Understanding what that beta-gamma delta label actually describes helps explain why that S-specific region behaves so differently from an ordinary, simpler sunspot group. A basic sunspot typically has a straightforward magnetic structure, one clear north polarity area and one clear south polarity area, arranged in a relatively tidy pattern that releases energy gradually and predictably. A beta-gamma delta region, by contrast, has intermingled areas of opposite magnetic polarity crowded together within the same compact sunspot group, creating enormous internal tension as those tangled magnetic field lines get twisted and stressed by the sun's constant rotation and internal plasma flow. When that tension finally releases through a process called magnetic reconnection, the energy comes out in a sudden, dramatic burst, precisely the mechanism behind every flare this region has produced over the past several days. The flare itself was only the opening act. That M6.9 eruption launched an Earth-directed coronal mass ejection. A massive cloud of magnetized solar plasma blasted outward into space. And later that same day, a second eruption. This one, a C4.7 flare tied to a filament collapsing on the sun's surface, launched yet another CME with its own Earth-directed component. 2 separate clouds of solar material launched hours apart from the same general region of the sun, both now making their way toward our planet on slightly different trajectories and timelines. Layered on top of those 2 CMEs is a third, entirely separate influence, a stream of fast solar wind pouring out from a coronal hole, a region where the sun's magnetic field opens up and allows charged particles to escape more freely than usual, is expected to begin buffeting Earth's magnetic field around midday on August 27th, with solar wind speeds climbing to roughly 600 kilometers per second as that stream arrives. That's a meaningful jump above the typical background solar wind speed of 300 to 400 kilometers per second. And it's arriving as essentially the opening wave ahead of the 2 CMEs still following behind it. NOAA's Space Weather Prediction Center has responded to this layered setup with a tiered set of forecasts, a minor G1 level. Geomagnetic-storm watch is in effect for August 27th, tied specifically to that incoming coronal hole stream. Then, for August 28th, forecasters have escalated that watch to G2, or moderate storm conditions, as the impact from the M6.9 flare's associated material combines with the coronal hole stream's continuing influence on the same day. Conditions are expected to reach active to storm levels, with the planetary KP index, the standard scale scientists use to measure geomagnetic disturbance, forecast to climb into the 5 to 6 range. That escalation is expected to persist into August 29th as well, with continued G1 and G2 level conditions possible before the disturbance finally begins to settle. This kind of layered, multi-day forecast reflects just how differently space weather agencies have to approach an event like this compared to a single, isolated eruption. Rather than tracking one clean signal with a defined arrival time, forecasters are essentially managing 3 overlapping influences simultaneously, each with its own separate timeline, and updating their guidance as new measurements come in from spacecraft positioned specifically to monitor incoming solar material before it reaches Earth. That constant recalibration is part of why the forecast has already shifted somewhat since the initial flare was first detected, with each new data point refining the picture of exactly how strong the resulting disturbance is likely to become. For anyone hoping to actually witness the effects of this spike firsthand, the timing genuinely couldn't line up much better. Aurora watchers across northern Europe, northern Canada, and the northern tier of the United States have been specifically flagged as likely candidates for visible displays during this window, since G2 level storm conditions are typically strong enough to push the aurora further from the poles than it reaches on an average night. Getting away from city light pollution, allowing your eyes roughly 20 minutes to fully adjust to the darkness and looking toward the northern horizon. After full dark gives you the best realistic shot at catching a glimpse, and pointing a smartphone camera at the sky in night mode often reveals faint color even when the display looks fairly subtle to the naked eye. There's a genuine element of uncertainty baked into all of this, though, and it's worth understanding why. Early modeling on the first CME suggested it might only deliver a glancing blow to Earth's magnetic field rather than a direct hit, and scientists have continued adjusting that prediction as more data comes in, since the exact speed, trajectory, and internal magnetic orientation of a cloud of solar plasma can shift in ways somehow are difficult to pin down precisely until the material is much closer to Earth. That internal magnetic orientation, specifically a measurement called the Bézet component, ends up being the single most important factor in determining how strongly an incoming CME actually couples with Earth's own magnetic field. When that orientation points sharply southward rather than northward, it can dramatically amplify the resulting geomagnetic disturbance in ways current forecasting simply cannot fully resolve until the cloud is almost here. Spacecraft positioned roughly 1 million miles from Earth, sitting at a gravitationally stable point directly between our planet and the Sun, provide the closest real-time look at the T-crucial magnetic orientation. But that measurement typically only arrives somewhere between 15 minutes and an hour before the material itself reaches Earth's magnetosphere. For a well-behaved single CME, that narrow window is usually enough to sharpen a forecast meaningfully in the final stretch. With 2 separate CMEs following each other closely, plus a coronal hole stream already influencing conditions before either cloud even arrives, that final measurement carries even more weight than usual in determining whether this event settles at the lower end of the G2 range or pushes into something stronger. Solar radiation is also part of this picture, even though it's stayed comparatively modest so far. The higher energy proton flux associated with radiation storms has remained below the threshold for even a minor S1 level event over the past day, with forecasters assigning only a 10% probability of crossing that threshold on any given day through the 28th. That's worth noting specifically because it means the primary story here really is about geomagnetic disturbance and aurora potential rather than the kind of radiation concern that would affect satellite operations or astronauts more directly. A meaningfully different risk profile than what a genuinely severe radiation storm would present for crewed space missions or polar flight routes. Zooming out from this specific event, it's worth understanding why a spike like this counts as genuinely notable rather than simply routine solar behavior. The Sun operates on an 11-year cycle of rising and falling activity, and while the current cycle technically passed its statistical peak roughly a year and a half ago, regions like active region 4513 demonstrate that the decline from solar maximum rarely happens in a smooth, predictable line. A single region producing 6 separate M-class flares within roughly 48 hours, one of them nearly reaching X-class strength, represents a genuine concentration of energy. Release the T doesn't happen every week, even during an active stretch of the solar cycle, which is exactly why this particular burst has drawn so much attention from space weather forecasters compared to the more routine, isolated flares that occur far more regularly. Regions this magnetically complex don't typically stay this active indefinitely either. The coming days represent a genuinely important window for researchers, watching to see whether this specific sunspot group whether this burst of activity represents its peak before the region begins gradually settling down as it continues rotating across the visible solar disk. None of this poses any direct danger to anyone on the ground. Even a full G2 or stronger geomagnetic storm carries 0 physical risk to human health, and the practical effects stay confined almost in tight. Rely to technology and infrastructure satellites experiencing slightly increased atmospheric drag, high-frequency radio user S facing brief degradation on the sunlit side of the planet, and, for the rest of us, simply a better than average chance of catching the aurora somewhere it doesn't normally reach, from Michigan and Wisconsin down toward the northern edges of states that rarely see any auroral activity at all under ordinary conditions. If you want to stay ahead of exactly how the IS spike continues developing, whether active region 4513 produces an actual X-class flare before it rotates out of its Earth-facing position, and how strong these incoming CMEs ultimately turn out to be once they arrive. Subscribing means you won't miss the update the moment NOAA confirms the details. Because based on everything scientists are currently tracking, this is genuinely the most active the sun has been in months, and the full picture of what this particular region still has in store is only just beginning to unfold, with forecasters continuing to watch every new flare and every subtle shift in this sunspot group's magnetic complexity for signs of what might still be coming before it finally rotates out of view.